Welcome to this training session about marine data for coastal monitoring. My name is Stefania Ciliberti. I'm a senior scientist at in Oceanic Weather Systems, and today in this video I will show you how to use QGIS for analyzing Copernicus marine products in coastal region to support the monitoring of coral bleaching event and eutrophication in coastal waters. Before starting with the implementation of the exercises, I would like to remind you that under Marine Data for Coastal Monitoring 2024 webpage provided by the Copernicus Marine Service, you have a dedicated section about QGIS that collects the video, particularly the exercises that we are going to discuss right now, together with some scientific documentation that helps you also in performing the technical steps towards the execution of the exercises, but also some supplementary material related on how to install QGIS and how to configure the plugins that we are going to extensively use during the training. So let's start by launching QGIS. I have already opened it, and I recommend you to save a priori the project in a dedicated folder under your working environment. This is an important step because from now on all the intermediate files that will be created by QGIS will be collected in this folder, and this will help you in managing it in case you would like to remove for some reasons. Additionally, you need to know that if this is not done, all the intermediate files are going to be saved under the working folders of QGIS, making much more difficult in a second step to clean out the files that you are not interested anymore to maintain. Okay, we save basically this exercise, and we use the Quick Map Service plugin to launch to integrate in your project a base map. In this case, for instance, once you click, you can search the specific source you would like to integrate. In my case, I would like to use the Google base map, in particular the Google satellite map, that is this one. We can close just for cleaning a bit the window, the other sections related on toolbox and the plugin functions for the base map, as I was showing you before. And now we are ready basically to start integrating the upstream data we want to use for the specific first exercise, that is related on how to monitor coral bleaching event, and particularly essential ocean variables like temperature and phosphate concentration in the area of Kenya Mozambique coastline that is characterized by coral reefs particularly stressed by, as you might imagine, because of the climate change. Through the Copernicus Marine website, you can access the Copernicus products, and the ones that we are going to use in this exercise are mainly related on the global analysis and forecasting system for the physical and biogeochemical components. So if you just go in the Copernicus website, you can access the products through the Marine Data Store. And as it is shown also by the colleagues of the Copernicus Marine Service in dedicated presentation, you have many ways for accessing the data through the graphical user interface or through the Copernicus Marine Toolbox. We are not going to detail this because this is the object of another tutorial, of another presentation. So we assume that for the specific area of study that we selected, both the two model products for the physics and the biogeochemical components from the global ocean forecasting systems have been downloaded a priori in our laptop. And now with the CMEMS NetCDF plugin that is accessible through the bar or through the icon here located, you can start to import the NetCDF files. This is extremely simple because you can use the the graphical user interface. I have here the data already downloaded for the Kenyan Tanzania coastline, and here the first product that I'm going to integrate is the temperature. So I do a right click here and I add it as a layer. Here you can see that specifically for this exercise I downloaded the available forecasting cycle as made available through the Marine Data Store on the 8th of June. This is because the main scope is here to see how we can monitor also the evolution in time, the forecast of the essential ocean variables that we are going to select in this region. So let's select all the time steps that we want to use in our exercise. These are intentionally downloaded only for the first level of the model at 0.5 meters depth, and we assign theta O as group. Theta O is the standard name for the variable as made available through the NetCDF file. We do add, and automatically these the list of files are visualized in the layer board, as you can see here, and of course these original data have been subsetted in the area of interest. Now let's import also the second file, that is the biogeochemical forecast for phosphate concentration. We select and we do open. Automatically the board is refreshed, and now we can select the variable and add it as a layer. In this case, for the same bulletin date, that is the 8th of June, we have the possibility to access a lower number of forecast data. This is because the two systems are working with two different processing chains, and I invite you to discover more through the Copernicus Marine Data Store, and in particular for the two products that we are here proposing, to learn more about the technical details, but also the scientific quality of provided product. Let's add again the list of layers that we have just preloaded thanks to the NetCDF plugin under the group PO4, and we can close now this. And as you can see, the two sets, the two groups of layers differentiated by variable are now ready to be used in the exercise. Now let's first of all, we deactivate the PO4, the phosphate concentration layer group of fields, in order to focus for a while on the customization of the maps for the temperature. And to assign a proper palette to the map, we select properties by doing right click on the layer, and a new window is open that gives you the possibility to modify the symbology of the specific field. In this case, we are going to fix the minimum and the maximum value of temperature according to what provided, I mean, for the specific time period. In this case, 26 and 29, we round to we round basically the minimum and the maximum value without keeping all the digits provided by the product. And as well, we can do a label precision up to 2 digits in order to make the reading of the palette easier for us. And let's use equal interval with the number of classes equal to 5. We can also change the palette. For instance, we can use turbo, but also the previous one could work, but you have a wide choice of color ramps for the customization of your map. Let's do apply, and once done, you can see that automatically the map is refreshed, showing where the area of higher temperatures are located, particularly in the offshore Mozambique and flowing towards Tanzania and then Kenya. So you have in this coastal area quite a higher temperature in the recent period. And to homogenize the palette also for the other available variables, it is sufficient to do right click, go to style, make a copy of the style, and then by selecting the specific layers, again redo right click and do paste style. In this way, all the maps related on temperature on sea surface temperature have been automatically refreshed by imposing the same colors and palette and minimum and maximum value of the palette as we performed for this first one. This will help a lot in reading the evolution in time, at least for this specific short period of the sea surface temperature, and make the monitoring much more effective. Okay, let's let's move to by deselecting theta. So by deselecting the sea surface temperature, let's focus now on the phosphate concentration. In this case, as you have seen simply by the overlapping of the two maps, both products are provided with different resolution. This is not, I mean, the fact that we use QGIS, Geographic Information System, for manipulating data related on in this case on marine products helps a lot, because you can exploit easily functions that can allow you to extract or interpolate different sources in a target region, or select the information at this provided resolution. So as we will see soon, this is extremely powerful and easy to be done. So let's do fastly a customization also for the concentration of phosphate. In this case, we do again styles. I'm not going to, sorry, properties. I'm not going to spend too much time in this case because basically the steps are the same as shown before. We go again in the customization of the minimum and the maximum value, in the definition of the classes for which we want to return the mapping of the phosphate concentration, and by doing that we can give a more appropriate color to this field. And now, very easily, we do a copy of the style by doing copy style, and we paste to the other field. And now basically all the fields are given with the same palette. Now with this we are ready basically to extract, to present the first way of manipulating this data or interacting with this data. And the first and the proposed, let's say, function is related on the extraction of essential ocean variables in specific target region. Do not forget to save, please, the exercise every time you have achieved a specific milestone in your execution. So the idea is to focus our attention in the coastal area of Kenya, Tanzania, where we have the higher concentration of coral reef, and monitor, basically extract the information related on temperature and phosphate concentration in this area. To do that, we first of all need to create a new layer, particularly a new shapefile. And let's assign to this shapefile a name. First of all, we save, we identify where we want to save the resulting layer, in this case under the working folder you are using. And for instance, let's call it Kenta's region, just to identify to give a name that easily recall you the basically what it contains, what is referred to. We save, and once done, we decide to select as a geometry type polygon, because we want to create a buffer, a region along the coastline where we want to extract progressively the temperature and phosphate concentration in order to monitor this kind of events of the coral bleaching event from an environmental point of view. We do OK. And now this new created layer has been added in your board. Let's drag outside the group of phosphate concentration, this new specific layer that we have been created. And now to properly work with it, to activate the possibility to use it, let's click on toggle editing. This once has been clicked, returns as information the fact that the layer is now open to be modified, and you can recognize this because you have the pencil here. But now to assign the shape, we need to add the polygon feature. And when you click again on this specific icon, another one will be automatically highlighted, activated. And you can choose how you want to digitize this, the area of interest. In this case, for instance, we can use the digitize by segment, because I want to, digitize by segment is this one, because I want to create the region where I want to focus my attention. You can, of course, draw the polygon as you wish, depending on the target area. Here is just to demonstrate how to use QGIS in this specific case. You add and specify an ID for this polygon, and now the polygon appears. If you are happy with this polygon, you can deselect the toggle editing. Automatically, the editing will be stopped and ask you if you want to change to save the changes in the layer that has been just created. Of course, we are interested in saving it. We click on save, and automatically this is done. Let's save also the main project in order to don't lose any important step in each of the different phases. Now we can customize also the view of this region, and this is done again by selecting properties. And in this case, I want to use one of the predefined style offered by QGIS, that is this one, that basically gives you the possibility just to see, first of all, the limits of the polygon that you have just created, but also the in background the fields that are under analysis, in this case the two temperature and phosphate. Now the next step is to extract the temperature and phosphate concentration only in the area in the Kenya-Tanzania region, coastal region, because it's where we want to monitor basically the evolution in time from the current day to the plus 10 days of forecast of the essential ocean variables. To do that, we select, right now we are working with raster fields, meaning that each pixel has a specific value. So we can perform this kind of extraction by selecting extraction by clipping the raster by the mask layer. So in this case, the mask layer is the area that we just drew before, and the input layer that we want to manipulate are the ones related on phosphate concentration and sea surface temperature. This is an example, on how QGIS can help in manipulating many rasters in input. This is done through the batch process. So if you select the batch process, you can automatically prescribe the rule that you would like to follow for performing the clipping of the input rasters over the area of interest by doing a selection from the open layers. So you can select all of them, of course, except the base map, and we do OK. They will be automatically displayed in the, here in the board. The system automatically recognizes the only available mask layer you just have created, that is in this case the Kenya-Tanzania region. So here we are going to keep the same the settings provided by default, so without specifying anything else particular, because we are just interested to perform a simple extraction of the essential ocean variables in this specific region. But I invite you to discover in the QGIS documentation also how the different fields here provided can help in manipulating even at higher levels these input rasters. Now let's save the clipped rasters in a dedicated, in the working folder, that in this case is QGIS exercises, the one that I'm using. And let's give a name, a tag here of the output files that will be produced once the specific function is going to run. So for instance, I want to call them, tag them with the keyword clip underscore, we do save, and QGIS asks you the way you want to autofill the file name of the output shape of the output layer. We can exploit different options. You can choose to do not autofill or fill with numbers, so the output will be ordered from 0 to n, depending on the total number of layers that are processed, or, and that is the option that we are going to use, fill with the parameter value. The parameter value in this case can be chosen among a huge list. Of course, my idea is to keep as reference the file name of the input layer. So the days of forecast for sea surface temperature and phosphate concentration. So we select input layer, we do OK, and you see that automatically under your working folder, the resulting fields will be saved with the tag clip plus the name of the original input layer. Do not forget, before running the process, to load the layer on completion, so you will display the results in your layers board, and after that you can run, and QGIS is going to work towards the extraction of the specific essential ocean variable in the target region. You will see that progressively the algorithm returns the number of processed fields, and on the layer board automatically is going to be refreshed with the newly created layers. Let's wait a couple of seconds until the algorithm is completed, and then we will see that the results will appear, and we can go further in the manipulation of the fields. Let's wait some seconds more. We are almost ready to visualize the final result. Okay, this is complete without any error. We do close, and as you can see in the area of interest, the fields, the corresponding fields that have been extracted are colored in using a gray color bar. Of course, I mean, now we can simplify the visualization of these fields. Let's collect all of them without showing the palette, because at the end what we would like to do to save time is to first of all deactivate the main fields, the fields that covers the wide region, and we keep only the specific ones that are targeting the coastal area. And let's copy the style previously created for the phosphate concentration over the overall region in this target area by doing copy and paste, and the same for the sea surface temperature. So we don't need to lose any more time in modifying the style. This will be automatically assigned according to the choices previously done. Okay, so now you have, you can even deselect the specific region, the bounding box that is not anymore needed. And you have now, in this case, the visualization of the sea surface temperature in the Kenya and Tanzania coastal area from the 8th of June to the 17th of June. You can reorder also the layers in the visualization by selecting the corresponding Manage Map button. Now, what we were proposing for this exercise is to use the basically a way of customizing again the map visualization for extracting or visualizing specific properties of the, in this case, of the sea surface temperature in the target region. We know from the paper of Wan et al. 2015 that the coral reef might tolerate, particularly for sea surface temperature, a tolerance range of temperature values below or above which they go in stress and they can be solicited by more dramatic events. They can, I mean, they might suffer for bleaching or even die. I mean, at all. So to apply, I mean, easily this categorization of the meaningful range of sea surface temperature that coral reefs can tolerate, that is from this paper imposed between 21.7 Celsius to a maximum value of 29.6 Celsius, we can do basically, we can exploit some statistical functions of QGIS for modifying the map accordingly. So let's go in, for instance, let's take one of these fields, the one on the 8th of June, that is characterized by higher, quite high temperature close to the coastline. Let's select again properties. And now in symbology, what we can do is to specify basically the limits that we want to visualize in our range, but also modify the settings of our map. So as render type, we are going to use again the single band pseudocolor. We impose the theoretical values as specified in the paper, 21.7 as minimum and 29.6 as maximum. Regarding the minimum and the maximum value settings, we specify that these are user-defined. So we are not going to make any specific statistical change on the minimum and the maximum value of the palette. We do as interpolation this time, instead of using the linear as used for the visualization of the maps, we use the discrete. Because here you can see that as soon as you change the way of visualizing the specific palette, this gives you the opportunity also to change the labels and target the analysis according to the specific limits you want to use for reclassifying the map. So in this case, for instance, I want to use only 3 classes, and I want to specify that the value below 21.7 are with a specific color that can be blue. Sorry, here we have the values between 21.7 and 26.9, and we can assign the color green because it's okay where the coral reef can tolerate this kind of temperature. And automatically for values higher than 29.6, sorry, here I have a problem, it's 29.6. Okay, and now for temperature higher than 29.6, for instance, we can assign the color red. Okay. And here we have, of course, this is being user-defined. You have to take care of this in modifying the labels and the values accordingly. Otherwise, the reclassification is not going to work. Okay. Okay, now the point is that for this specific day, we have never temperature higher than 29.6, so automatically the palette will stop on that. But this is just to set up the color map of this discrete way of manipulating the data. We do OK. And of course, I mean, since we know a priori that in this region the temperature is for this specific day is never higher than 29.6, the map will be colored with in green. Then you can, as before, copy the style and apply to all the others. And basically, I think that for this specific region, quite recent, we don't have events that solicitate the coral reefs with such higher temperature. So you will see that progressively the map will return always the green, meaning that the region is, let's say, safe, in a safe condition. Of course, you can modify and depending on the specificity of the region, calibrate the minimum and the maximum. This is something that the people that are in charge of coastal management for the monitoring of the ecosystem health in the area, being expert, can specify much better in order to produce maps that are more consistent with the specific tolerance ranges of the coral reef that live in this region, and produce every day by integrating the Copernicus marine data in QGIS, produce maps that can easily provide information about the ecosystem health and particularly for monitoring potential coral bleaching events that can occur in the area of study. The same type of reclassification of the map can be done also for the phosphate concentration, following the prescription that are provided in literature, again by the reference that I proposed you in the document. But the same conclusions said before for sea surface temperature are also valid for phosphate concentration. So I'll leave to you all the task to complete this first exercise and apply also the reclassification for the phosphate concentration. We save the exercise, and now we can basically close this project and move forward with the second one. Let me clean a bit the board. So let me create a new project. Let me save it as exercise number 2. Let's load again this map. Okay. So let's move in Europe, in one of the region that is particularly affected by eutrophication, that is the Northeast Atlantic and the Western Mediterranean. But not only, also the Black Sea and the overall Mediterranean are characterized by eutrophication events. And let's see how we can use the Copernicus marine data, in this case the ocean color satellite L4 observations provided by Ocean Color TAC, and the two products, model products provided by the Mediterranean Forecasting System and by the Iberia, Biscay, Irish Analysis and Forecasting System. Again, all the different products are accessible through the Copernicus Marine Data Store. So in this case, I'm referring to the Ocean Color product and the Atlantic and the Mediterranean model product for the physical component. Here it's for waste, but just to show you being preloaded the extension of the EB region and the extension of the Mediterranean domain. Particularly, we want to focus our attention on the Ebro Delta, that is having, a big specific hotspot for biodiversity in the Mediterranean Sea, and most of the time along the year the region suffers for harmful algal bloom. That is a consequence of the eutrophication in the Western Mediterranean. So the idea is to show how we can use QGIS for monitoring the concentration of chlorophyll in the region of interest, but also how to provide support by using the model products in understanding what is the evolution in time of salinity. That is an environmental variable that is extremely important for monitoring eutrophication events. Okay, also in this case, I have pre-downloaded the Copernicus marine data. So what I'm going to do again is to load the netcdf files using the plugin. So I import the netcdf through the CMEMS plugin. I guess that I have it open here exactly. So this is the reason why I don't see the pop-up. This time I go in the Ebro folder that I pre-created before. Of course, if you have any question on how to download specifically this package of data used for the two exercises, do not hesitate to contact the Copernicus Marine service and the training team and we will provide the help in case also the information provided in the document might be not sufficient for you. Let's first load the ocean color product, the satellite product. Here we have the concentration of chlorophyll and I add it as a layer. And I select, by doing control and selecting each one, the monthly chlorophyll concentration from June to August 2023. Okay, and it will appear in the region of interest, that is this one. Now it's quite easy to be seen, the region. It appears automatically. Sorry, there was still the previous window open. Okay, now let's load the salinity, sea surface salinity from the Mediterranean Analysis and Forecasting System for the physical component of the ocean. And we add as a layer. In this case, I have downloaded again the monthly means sea surface salinity from June to August 2023. I do a selection in only for the first level of the model at 1 meter depth. And in this case, since there might be some collision with the names between EB and MED products, I'm going to specify that this group belongs to the Mediterranean domain. So I rename the group as SO-MED, _MED. I add it. Okay. And finally, I'm going to load the EB product. Let's add the layer again. And we select again the three monthly means value for sea surface salinity. This time for the EB model, sea surface salinity is given for the first level of the model at 0.5 meters. So there is a gap, a difference in depth between Mediterranean and EB product for sea surface salinity of half a meter. That is something to keep into account, when we are going to interpret the results. And as done before, we assign to the group the name with the tag EB. We add and we close. Okay. So now you have the three sources of data, of information. Let's very briefly modify the property of the map. In this case, I specify the concentration. I mean, I'm not going to make any specific change to the minimum and the maximum value, but simply conserving and rounding them using, in this case, 5 classes. So we apply this. And if you deselect, you have much consistent palette for this specific variable. Let's do a copy and paste of the style to the other maps. Now let's go to the salinity from the MED. Okay. Let's activate it. You see that here the salinity, I mean the model is at 1/24 of a degree, so it's not fully resolving the small structures given by the base, like fungal calf's base, but it's still providing valuable information of the water conditions in the target mass of interest. And now let's modify the properties. We use as color ramp, I mean, we can use Viridis, for instance, I mean, any or plasma, the ones you like. Okay, and let's specify the minimum and the maximum. So in this case, the minimum and the maximum value for the sea surface salinity in the region from the Mediterranean spans between 35 and 38 PSU. Very quickly, we apply the same settings as before to the map, and we copy the style to the other set of layers. So basically here you see that in the delta there is a plume. To have a consistent comparison between the Mediterranean and the EB region, I'm going to apply the same palette defined for the Mediterranean to the EB product. So I'm going to copy the style and paste it. And now I will show you that differently from the Mediterranean, the EB product is reconstructing a plume that is much wider, is fresher and wider with respect to the Mediterranean ones. And this is because of the differences in the model configuration. So if you want to investigate more about the differences between the two models, I encourage you to go into the quality information document and product user manual, and you will see how the two systems treat rivers as surface boundary conditions in the two model configurations. These are quite different, but of course this opens a lot of opportunities for analyzing, for intercomparing the model output, investigating from the scientific point of view the main reasons of this behavior, and also validate against the available in situ observations in order to understand which of the two models is performing better and is providing a reconstruction of the sea surface salinity in this specific time period with more accuracy. But of course, this is not the scope of these exercises, despite we will see that through the profile tool plugin, we can somehow extract this information, also because the stakeholder can be interested to understand the differences between the two model products that can be used in any ecological model that is as consequently used in the area of interest. Now, after this, let's say, overview of the upstream data, let's go now on the first, let's say, task, that is the characterization of the chlorophyll concentration in the Ebro Delta and in the coastal area. We know that as well as for the coral bleaching, it's fundamental when we talk about eutrophication to monitor the essential ocean variables as observed in the target region, but also as modeled, predicted by the operational forecasting system. So the first function that we are going to consider in here for characterizing the chlorophyll concentration in the two bays of the Delta del Ebro, having the advantage of the very high resolution of the satellite product, is to basically extract in specific points of interest the value of chlorophyll concentration and save them in a dedicated layer for performing in a second step potential statistical analysis. So let's use again let's invoke layer. Let's create a new layer, a new shapefile layer. In this case, we save them under the local folder we just created before, and we call it Ebro points. Ebro points because I want to select some specific station or points of interest for extracting the chlorophyll value from the satellite product. Okay, after specifying the name of the new layer, I also have to prescribe the geometry type that is point. I spoiled it before. Okay, now I can click on OK, and you see that this new layer appears in the layer board. And I want to take it out from the specific group of physical fields that I just previously created. To activate it, so to allow it the modification of the Ebro points layer, I select again the toggle editing, and I then move to add the point feature, because my scope now is to digitize the points where I want to extract the information for the chlorophyll concentration. And in this case, I can digitize them. For instance, I can give an ID 1, 2, and 3. I mean, in Fangar Bay, in the document that I provided with in the QGIS material, I also included the other bay. Okay. Anyway, now I just, for sake of brevity, select 3 points. I deactivate the toggle editing, saving the result, and now the layer will come back without the possibility of modifying it. Now, the next step that I want to do is to extract the chlorophyll data in these digitized stations. So to do that, I'm going to use one of the processing functions made available by the toolbox, and the function that I want to use is sample rest value. Sample rest values. Okay. Now, again, the function returns a window, and if you have just one layer, you can easily specify the input layer, the raster layer, and the output. But if you have, as we have in this case, more than one layers to analyze, we can invoke the run as batch process and select as raster layers the fields, the layers that are currently loaded in QGIS. In this case is the surface concentration of chlorophyll from June 2023 to August 2023. and automatically being the input layer specified just now as points preloaded in this form, this will be automatically applied to all the layers that we want to process. Now we need to provide the name of the output. In this case, for instance, I can assign a tag point underscore for the output. I save it, and I want to fill the output file name with the parameters value, assigning as main root the raster layer. So basically what I expect from this procedure is to have the output with the tag point underscore and the name of the chlorophyll fields previously preloaded. And indeed, this is the case. Under, of course, the working directory. Again, do not forget to load the layers on completion and run it. So now, in this way, basically for each of the 3 monthly observations of chlorophyll, as we were loading at the beginning, we have the corresponding extraction of the points, of the values at the point location. And indeed, if I select I do right click and I open the attribute table for the 3 specific timestamp, I have the corresponding value of the concentration of chlorophyll in the 3 points for, in this case, August 2023. So we can monitor basically which are the stations that can be affected by the higher concentration of chlorophyll. This type of table can be further exported in CSV and make an intercomparison with the observed corresponding observed essential ocean variable from satellite or even from the model, so to support validation exercises. I'm going now to show you the last plugin, very powerful, that is the profile tool that, as I was saying to you before, supports the user to, let's say, extract information from the raster layer and consequently export the specific values just extracted with the tool in tabular format to be further elaborated. So the profile tool, that is a plugin offered by the community, is extremely immediate in the usage, and in this case, for instance, I first have to specify the layer I want to manipulate. In this case, it's okay, the layer I want to analyze is for, particularly the sea surface salinity in June 2023. Now, the profile tool basically gives you the possibility interactively to specify a starting and end point where I want to extract the information of sea surface salinity. So in this case, what I do is to do Okay, the profile tool is a way to visualize the specific distribution of in the space, or in this case for sea surface salinity, from the available active layers. Okay. So I select the first layer that belongs under the Mediterranean, and for instance I assign a color, for instance the green. Okay. After double clicking to both and adding them into the profile tool dashboard, I assigned the green color to the MED source and the red color to the EB source. Now I can draw the line, I mean the transects or the section that I want to monitor basically, and the distribution of sea surface salinity along this line are easily displayed in the dashboard. So you will see that in this case the EB product has a lower salinity in the just at the Ebro mouth, basically of about 28 PSU, while the Mediterranean has a value of about 37 PSU, so quite higher than the EB region, the EB product, sorry. And so you can do also other kind of transects, for instance, in this case, that are perpendicular to the coastal zone. And here again, you can appreciate that moving from the coast to the from offshore to the coastline, the salinity from the two model sources are quite different. In this case, we have different, but not dramatically different, in the region just outside the Fangar Bay. About 36 PSU is given by EB and 38 by the Mediterranean. The toolbox provides also the possibility to save the specific query as a PNG, so as a picture that can go in a specific document, in a bulletin, for instance, or as tabular format to be further analyzed or imported in other computing environment for performing other statistical analysis or other specific diagnostics that might be relevant for monitoring the conditions of the ocean state in the coastal ocean state in the region of interest. So I hope that this webinar, this tutorial was useful for you, that inspired you for exploring more the functionalities of QGIS. So thanks a lot for watching it, and for any question, please do not hesitate to contact the Copernicus Marine Service, and particularly the training team, as well as routinely check the last updates in the dedicated page of the training workshop for the marine data for coastal monitoring. Thank you very much.